Hello students. So today we will discuss order of an element. What is order of an element? If G is a group under the operation star with the identity element E, then order of A is the smallest integer n such that A raised to power n give us identity. The smallest such integer which make A raised to power n identity is known as its order, or you can say when we multiply a n times, because here the operation is star means product operation we have taken as default operation, and if a is multiplied n times with itself and give us identity, and n is the least or smallest such integer, then n is known as order of the group. And by closure property we know that all these times, how many times we multiply a with itself, the result must be the element of G. Now order of an element is denoted by order of A, or it can be written like this, mod of A. So if there does not exist any integer which make a raised to power n is equal to identity, that means A is of infinite order. Now let us see some simple examples. In a group of four uh, numbers, 1 minus 1 iota minus iota, which we have already proved it is a group under the multiplication operation with the identity element 1. Now we have to check for the order of each element, like 1 raised to power 1 is 1. We have to raise the power of these elements which make it equal to identity, that means equal to 1. So minus 1 raised to power 2 is 1, iota raised to power 4 is 1, minus iota raised to power 4 is 1. So these are the orders, order of 1, order of minus 1, because these are the least power. We can have minus 1 raised to power 4 as 1, but 4 is not least is 2. So order is the at least positive integer which make it equal to identity. Similarly, in the other group 1 omega omegas, you can find the order of each of the elements. And one thing you will notice here, that the order that we have found for each of the elements here does not increase the order of the group. That is a very important result. We will prove it in a later stage, but here you can just see that of order of an element, of any element of that group, does not increase the order of the group. Here the maximum order is 4, order of the group is 4. Here also the maximum order of the element is 3, and the order of the group is also 3. Now for addition, so these things we have discussed for the multiplication operation. If the operation is addition, then order of an element is the smallest integer n such that n into a is equal to 0. So when the operation is addition, then we have to add a n times, and if it give us 0, then n is the order of a. Right, now for addition operation we can check. This is the example of addition modulo 6, which contains 6 elements, and now we have checked the order for each of the element. So here we have to write all the elements 0, 1, 2, 3, 4, 5, and we have to find the least integer which when multiplied with that element give us 0, because the identity element here in the group under addition, or in this addition modulo 6 group, 0 is the identity element. So 1 into 0 is 0, then 1 is the element. We have to multiply it with some number which give us 0 as answer. So this number will be the order. So the least number when multiplied with 1 give us 0 is 6, because this is addition modulo 6 group. So we have to write the remainder after dividing by 6. So remainder becomes 0 only if this number is a multiple of 6. So multiple of 6, least multiple or the smallest multiple is 6 itself. Similarly, we have written all the orders of different elements. Now for this group of real number except 0, you can say that this is a group of non-zero real numbers under multiplication. So in this group you can see only 1 and minus 1 has order, because these numbers 1 raised to power 1 is 1, 1 is identity. Here the identity element is 1. So 1 raised to power 1 is 1, that means order of 1 is 1. Minus 1 raised to power 2 is 1, so order of minus 1 is 2. But for all other real numbers, let r be the real number, and we have to find the power of r which make it 1. But there is no such positive integer which when raised to power r give us 1. So all other real numbers are of infinite order except 1 and minus 1. These are two element of finite order. All the other elements are of infinite order. Now in this group of complex number, non-zero complex numbers under multiplication, we need the number n such that z raised to power n is 1. So that is the property or definition of order. So what is such n? Can we find this? Yes, because this equation is soluble for complex number, and this we can solve by using De Moivre's theorem. So these are nth root of unity. So there are nth root of unity. So therefore we can have many elements which have order n. So these are soluble. Now this is the general linear group of order 2. That means here we have to take the 2 by 2 order matrices whose determinant is non-zero, right? Now the identity element, because for order we first of all we need the identity element. Now we have to check the order of a few fixed elements or few particular element like a, b, c. We have taken these three elements from general linear group. So a when multiplied by a square will give us identity. That means order of a is 2. So a raised to power 2 is identity. Similarly, b squared becomes 2. We can check here the product, and therefore order of b is 2. Now for c, when c is multiplied with c, we get this as a result, and it is not identity, so we have to continue multiplying it with itself, so unless we get the identity element as the result. So when c multiplied c square is multiplied with c, that means c cube is 1601, and continuing in this way we can see that there is a relation between the power of c and the number here, right? The number here, not this one. This is square, here 4. If cube we get 6, and that means if we have multiplied it n times, c raised to power n will give us 1 2 and 0 1. So that is not going to be identity at any stage. When we multiply c with itself, it's not going to give us identity as answer. Therefore this element c does not have the order. The order of c does not exist, where the two element has order but the third does not have the order. So now see this group. This is again a group under modulo here it is multiplication modulo 8. The element are 1 3 5 7, because we have already done that for multiplication modulo group we have to consider all the elements which are less than 8 and co-prime with 8, which does not have any number common or common factor with 8. So these are the numbers. So we have proven that it is a group. So now the order means all the four element we have to raise power such that the answer is identity, means 1. So 1 raised to power 1 is 1, that means order of 1 is 1. Now you can see 3. If we multiply 3 with 3, 3 square, it is 9, and 9 when divided by 8 give us a remainder as 1. So 3 square is 1. that means order of 3 is 2. Now similarly 5 square 25, 25 when divided by 8 give us remainder 1. That means this is again 5 square is 1, give us identity. That means order of 5 is 2 and order of 7 is 2 in the same way. So this is the way of finding the order of different elements, and we have few theorems about them, so we will solve it them later. Here now the next group is group of permutation S3. So there are 6 elements in S3 and we have to find the order of each. So when first element, that is I, the identity permutation when raised power 1 give us identity, because here this is not 1, this is identity permutation I. So we have to increase the power of each element in a such a way that the answer is identity permutation. So here we have 1 2 element, and when we increase the power 2, increasing power 2 means multiplying it with itself. Like here when we multiply this 1 2 with 1 2, it means we have to multiply in this way 1 2 3 and 1 2 3. We write both the permutation 1 2. The first cycle means image of 1 is 2 and image of 2 is 1, and 3 has image 3. Similarly in the second, because the permutation is same 1 2 1 2, so image of 1 is 2, image of 2 is 1 and image of 3 is 1. Now when we multiply them, we write 1 2 3 the element as it is. Now we are going to write the image that will be the product of these two. So first of all we see the image of 1 from here. Image of 1 is 2 and image of 2 is 1, means image of 1 is 1 we get. Now for 2, image of 2 is 1 here and image of 1 is 2, so image of 2 is 2, image of 3 is 3 in both, so it is 1 2 3. Image has 1 2 3 respectively, that means each element is its own image, that means it is an identity permutation. So when 1 2 multiplied with 1 2 we get identity, that means 1 2 square is identity permutation, means order of 1 2 is 2, right? In this way we can find the order of each of these permutations by multiplying them in a expanded form. You have to write the expanded form, like here you can see this result 1 2 3. First of all you write 1 2 3 the elements. Now we are going to write the image according to this relation. 1 2 3 means image of 1 is 2, image of 2 is 3 and image of 3 is 1, because image of the last element is the first element. Similarly here the same element is written here, so this is the product 1 2 3 with 1 2 3. Okay, you can write to expanded form in this way. Now we have to write the answer. What will be the answer here? So first you will see the image of 1 in the second permutation. Image of 1 is 2. Now we have to write the image of 2 from the first. The image of 2 is 3, so we get the image of 1 is 3. Now image of 2 is 3 and here the image of 3 is 1, that means image of 2 is 1. We have to combine these two. This is called composition of mapping. Now next the image of 3 is 1 here and image of 1 is 2 here, so image of 3 is 2. Now if we write it in a cyclic form, so this will be image of 1 is 3 and image of 3 is 2 and image of 2 is 1, so it is 1 3 2. So their product means 1 2 3 square is 1 3 2 as the answer. This does not give us identity, so that is why 1 2 3 square is 1 3 2, not the identity. Then we have to multiply it again with itself. 1 2 3 cube, 1 2 3 square is 1 3 2, and when it we multiply it with one more 1 2 3, that will give us identity. You can easily check this. That means order of 1 2 3 is 3. Similarly for 1 3 2, you can check by multiplying it in an expanded form, that its order is 3 again. So this was all about order. Thank you.